Okay, we are recording. All right, so I just want to announce that in case you have questions about anything, I am going to hold I guess, a virtual office hour this week. So Friday at 11 a.m. And so feel free to join, ask questions. I'm not planning any, special review or anything like that. It's just really to answer any of the questions that you may have. Okay. And we'll go as long as there are people asking questions. So we'll do that this week. Okay. All right. So today we will polish off the rest of this thermodynamics chapter or thermochemistry. And this is where we ended yesterday. Talking about using calorimeters and talking about heat capacity. And so this is an equation that you will be given. Okay, so again, you'll be given all the equations, all the constants that you need on the exam, so no need to memorize anything. And so there are two versions of specific heat heat capacity. There's specific heat, and then there's the molar heat capacity. And so this is the variety if you have a mass, okay? And so this value will be in a certain unit where you're given grams in it. So, whoops, over here. Okay, so the unit for that would be joules per gram degree C, okay? But if you have a question where you're given molar heat capacity, so that's just the same equation really. It's C m delta T, except this now is moles. Okay, then this unit will be joules per mole degree C. Okay, so just really look at the question. And if the units that you're given for heat capacity is this, then you're going to, have to use moles. So you'll have to convert usually grams to moles in the question. But if you're given this directly, then there's no need to convert anything. Okay, so I'll show you in this next slide kind of the questions to expect related to these, but it's pretty simple. You usually just, plug and calculate. Okay. All right. So those are kind of the two versions. It's the exact same formula, just kind of different units. Okay. Either grams or moles. Okay. So here is one variety of a question. Okay. So assuming a can of soda has a same specific heat as water, and I would have to tell you that. Okay. So in the question somewhere, I'd have to tell you that that is the heat capacity for water. Okay. Calculate the amount of heat in kilojoules transferred when one can is cooled from a certain temperature to a certain temperature. Okay, so the temperature change in this is always going to be, I guess I should have written it out, that's final minus initial. Okay, so the final temperature that it's at is 3 degrees Celsius minus 25. Okay, so in this case, you're going to actually have a negative value for this delta T. Okay, and so the equation, it's just Cm delta T. So C, you just plug in 4.18 joules per gram degree C. Okay, the mass is 350. And then you have minus 22 for degrees Celsius. Okay, so then you just confirm, you confirm all the units cancel. Okay, and so then you should end up with just so many joules out of that. Okay, so you just kind of plug it in. Okay, and I guess it was asking in kilojoules. Okay, so if you calculate it out, you get like 32,000 joules, okay? And then remember that that is just 32 kilojoules, okay? So minus 32 kilojoules, okay? So in that case, so you have a negative value, okay? So what do you think that means as far as is that, well, I guess it says right here in the slide, doesn't it? So heat evolved, okay? So that means that it's exothermic as far as the system is giving out heat to the surroundings. So system is releasing heat to the surroundings. Okay, so that's what that negative sign means. If it's positive, that means that the system, in this case, what, a can of Coke or something, is absorbing heat from the surroundings. Okay. Okay, so that's kind of a simple variety where you just have one kind of system, and it's either absorbing or releasing heat. Okay. I did post a bunch of questions to Chem 101. So somewhere in Chem 101, when you log in, you should see like a homework option. Okay. And so you've got until the exam expires, basically. So until 11:59 on Thursday to do these questions. Okay, so I put 19 questions on there. You don't have to attempt them all, but it'd be good to look at these. So again, these are questions that you haven't been tested on yet. So again, to kind of study for the final, I suggest going back through all those, practice midterms, look at the solutions to the actual exams, because your final will be drawn from that same pool of questions. And then these are some others that came after midterm 3. Okay, so this stuff that we're doing this week, and then really that stuff really from last Friday's lecture, so the valence bond theory stuff. Okay, so in here, I posted kind of a more complex question. This one. Okay.
I had a question.
Oh, yeah, sure. Yeah.
Yeah, so I guess are the homework grades been are these going to be considered as credit no credit basis, or are they gonna I know homeworks are graded.
Yeah, these are really optional. Yeah, so if you do them, cool. If you don't, that's fine too. It's not going to influence your grade at all. Yeah, because your Chem 101 is just really on participation, and so again, if you've attempted at least half of the in-class ones, you're going to get your full 3%. And so this
Okay.
is yeah. Okay. So this question, you've got a lot going on here. So you've got a metal that is changing temperature, and then you've got water that is changing temperature. So basically, you've got kind of this, I don't know, I guess a calorimeter. So let's say like a styrofoam cup, something like that has water in it. Okay. And then you've got this piece of metal, let's say this cylinder of metal, that is at, 96 degrees Celsius. And this water is at 26. Okay, and then you put this hot metal into the cool water, and not surprisingly, this will go up. Okay, so it's now going to go to 28.1. Okay. And you're supposed to find out, what is the identity of the metal. Okay, and you're given all the different specific heat capacities here. So, any ideas how to approach this question? So the equation is still that. Okay. But the way to approach a question like this is that Q of the metal, so the heat that's being released from the metal, so I guess there'll be negative Q, right, because it's exothermic, is going to be the same heat that is absorbed by the water. Okay, so does everybody kind of get this? Right, the magnitude of that heat is going to be the same. It's just kind of, the flow, if you will, of heat is different, right? Because it's being removed from the metal and going into water, right? Because this is going up and this will go down in temperature. Okay. And so you just fill it in, right? So this is going to be negative Cm delta T, okay, and we'll say that's for metal, is equal to Cm delta T for water. Okay. And so here, to get the identity of the metal, we're really solving for this one. Okay, so we don't know what that heat capacity for the metal is. So that's going to be our variable. Okay, so we're just going to plug everything else in. So minus, and then we don't know C. The mass is 150. And then delta T, what is the delta T for the metal? Any ideas? How do we figure that out?
Is it going to matter though? Because like it should be possible.
Yeah, so
would it be? Would the final temperature be 96 minus 28.1?
it's actually just the opposite of that, really. So remember, so it's so final minus initial, right? And so
Final minus initial.
yeah, so the final temperature of the water is what it's going to equilibrate to, right? Oh, did I do the wrong thing? Oh, yeah, I did. Yeah, sorry. Somebody just said I screwed up already here. So the 150 grams is actually water's mass. So thank you, Catherine. Yeah, thank you. So that should be 80 grams, right? So you have 80 grams of the metal. And then, yeah, so for the temperature change, it's going to, the final temperature is 28.1. So it's going to be 28.1 minus what it was originally. So 96. Okay, so what is that? So 28, let's see. So 28.1 minus 96. So that's minus 67.9 degrees Celsius. Okay. And then on the other side, for water, we're told what that value is. Okay, and then mass, that's the 150 grams. And then running out of room here. Delta T for that is going to be 28.1 minus 26. Okay, so 2.1. All right, so then we kind of just plug everything in. So therefore, C for the metal, okay, is equal to 4.18. 150 times 2.1 divided by 80 times 67.9. Okay, so these two negatives cancel. Okay, so everything is then a positive value. Okay, so then if you work that out, 4.18 times 150 times 2.1 divided by 80 times 67.9. So you get 0.0 3 sig figs, 242, and that would be joules per gram degree C. Okay, so what do you think? So what metal, move the text box here.
Closest to silver.
Yeah, so it's closest to silver. So therefore it is silver. Okay. So any questions about that? That is as difficult as these questions get, really, where you've got, something that's losing heat and something that's picking up that same amount of heat.
So how different can the specific heat capacity that we find be? How different can that be from the one given to us? Like if it were 0.26, would that be unreasonable?
Yeah, it's usually pretty close. Like, this one was what, within 0.01 or something like that. So yeah, it should be pretty close to these. I'm never going to put a question on where it's excuse me, between two of them or something like that. So it'll be very clear. It's usually like bang on or very close. Yeah.
Cool.
Okay. All right. So any questions about that variety then? So that's, really the toughest that you could see. Not to say I'll put one of those on, but yeah, you never know. If it were the ACS final, they love these ones. So yeah, you definitely have one of those on there. Okay. The question, why wouldn't you use 26 degrees? Yeah, let's go back to that question. Yeah, so to calculate the final, so it's final minus initial, and so for the metal, the final is actually going to be this. So that's the water, so the final temperature of the water. So that's why you did 28.1 minus 96, the initial temperature of the metal. And then we actually did use 26 for the water, right? Because that was its initial temperature, and then that was its final. Okay. All right. So now let's talk about Hess's law here. And Hess's law means that you can have an overall reaction that's composed of a bunch of steps. And if you know the energy that's released or absorbed by all of these steps, you can just add them up and get the total enthalpy change. Okay, and so let's say, if this is the overall exothermic value, so this is releasing 92.2 kilojoules of energy, then you can determine what the energetics of, let's say a separate step is. Okay, and so the way to do that would be you just take your total, so minus 92.2 is equal to essentially delta H1 plus delta H2. Okay, and so if we know this one, minus 187.6, we don't know that, so we'll just say that that's X, right? Then we can say that X is equal to minus 92.2 plus 187.6. Okay, so you're just really solving for X here. Okay. All right, and so that will be 95.4 kilojoules. Okay. So does everybody see kind of the strategy there? So, again, the variety of questions you'll see is I'll either give you this first step, give you that second step, and then ask what is the enthalpy overall. Okay, and then for that, it's very simple. You just add them up. Okay. This is kind of the more, less direct question. Okay, where you're given this total, and then you want to know, like, what's one of the steps here. Okay. All right. Now let's talk about what you can do to add these different steps up. So on the Chem 101 questions, here we go. Okay, so there are two things you can do to an overall reaction. Okay, so there are two operations that you can do. There is where you're multiplying it through by a certain coefficient. Okay, and so does everybody see, if you're given this value, okay, so you've got this enthalpy that's exothermic, and then it's asked, what is it for this one? Does anybody, do you want to take a guess? What do you think you would do for this? Anybody?
What are we trying to find?
Yeah, so you're trying to find the enthalpy for this one. Now it's, you're going to multiply by something. It's actually just multiplying by 3, though, right? So this one is 3 times what this one is, and so you just multiply this value by 3. Okay? So if you multiply I guess I should say reaction by a coefficient, then you multiply the enthalpy value by that same factor. Okay? So, if it's 3 times, then it's going to be, what is it? So 3 times minus 79.2. So what is that?
So what do we do if not everything in the second reaction is 3? Like, what if the H was 3 and the F was 2?
Yeah, for that one, you wouldn't be able to tell without more information. So the questions you'll get, they will be all multiplied by something. Yeah.
All right.
Yeah. Okay. So that's so that would just very simply be, a negative, right? So minus 237.6 kilojoules per mole. Okay. So that's one operation. Now, what do you think you would do to this same one? What would it be for this? Let me write it like this. Goes to H2 plus F2. So what do you think? So what would it be for this? What is the delta H for this?
Would it be negative 79.2 divided by 2?
No. Yeah, that would be, so that one, it would be this. That would be 1/2 H2 plus 1/2 F2 goes to HF. Then it would be like delta H original divided by 2.
Since you're going backwards, wouldn't you just do positive 79.2?
Yeah, exactly. Yep. So in this case, you're not multiplying by anything, but the second operation is if you reverse it. Okay, and in that case, you just flip the sign. Yeah. So you have plus 79.2. Yeah. Good. Okay, so let's see. I have a question where you kind of put stuff together here. What about this one? Show it larger here. There we go. Okay. So oftentimes you'll kind of have to do both of those operations, right? So if you're given this one, how do we get this? So what operation or operations are you doing? So first off, are you flipping it? So what do you think? Do you think that this one that you're interested in is the reverse of this?
I think you would have to reverse
It
it.
is, yeah, it is, because now, in this one that you're given, calcium oxide is a product, right? But it's a reactant in this one. So the two operations is that you're going to reverse it, okay, and then you're going to multiply by 2, right? So everything above is 2, right? 2 times a half is just 1. Okay, so you're going to multiply by 2. Okay, so for this, if you reverse it, it's going to go to plus 635, right? You're reversing the sign. And then you're going to multiply by 2. Okay, so it's going to be 635 times 2. So plus 1270. Okay. So any questions about that? That's, a couple operations. Again, you're only going to be doing those, either reversing it or not, and multiplying by coefficient or not. Okay. And then I think the last one I have related to this is this one. So what do you think here? So now you're given 2 equations and you want to know kind of that overall for it. Kind of tricky, isn't it? I'll rewrite them here. And this helps too, if you rewrite them, and then you can see what you need to do to, add them up appropriately. I think it helps. There. Okay, so what do you think about that first equation? So are you reversing it?
Yes.
Yep, you are,
Also
right?
divide it by 2.
And yeah, so you are reversing, yeah, so it's reversed. And then as far as the coefficient, this has a 4, but that has a 2, so you actually have to multiply by 2, right? Okay, so maybe if I just do it like this. I don't know why it's such a thin thing here. Okay, there we go. Okay, so reversing it and multiplying by 2 means that it is 4HF goes to 2H2 plus 2F2. Okay, and then your value is going to be plus 79.2 times 2. Okay. And then, are we doing anything to the second equation?
Would we also reverse it and divide by 2?
Are you reversing it?
I don't think so.
No.
How do I know if I should reverse it?
Just look at, if you have a reactant over here, is it still a reactant in the overall? Okay, or a product, right? So these ones are kind of staying put, right? So that's still a product, this is still a reactant. Okay, so you probably don't have to do anything there, right? So then I guess if you're just looking at kind of like adding them up as they are, the fluorine goes away, right? And so I think we have it right? This stays the way it is, so that's plus 141.3. Okay, so we've got carbon, and then we've got that 4HF, the 2 hydrogen, and then the CF4. Okay, and so then the overall then will be that 79.2 times 2. So that's 158.4 plus 141.3. So that's 299.7. Okay. So let's see. Yeah, or 300, I guess. Yeah. So. Okay. So again, that's as complex as you'll get, really, related to Hess's law, really. Okay, but just kind of look to see if in a particular step, do you keep products where they are and reactants? Sometimes, for instance, what kind of threw people off, I think, is that fluorine is in this one, but it doesn't appear in the overall. So that just means that it's going to be canceled, like it's reactant and product, so they go away. Okay. All right. So Hess's law, we're not going to go into this in any big detail. In 132, we get more into this, but this is just showing you that what are called Born-Haber cycles. It's something that describes the energetics behind dissolving or forming a salt from its elements. Okay, and so in this case, this is how much energy does it take to form sodium chloride from its elements. And so this is the overall reaction where you've got sodium and chlorine to form sodium chloride. Okay, and so overall it is exothermic, so minus 411. So overall, again, you're looking at your final minus initial point. So this is your delta H. Okay, and then as far as Hess's law here, these are all your steps. So these are your endothermic steps, so ones that require energy. So this one, you're vaporizing sodium, so you go from solid to gas, and then you break apart chlorine molecule into a chlorine atom, and then you ionize the sodium. Okay, so at this point you've got sodium plus and Cl, okay, and then you have to get adding an electron, so an electron affinity of chlorine, okay, and these steps release energy, okay, so you have all the ones that require energy and then those that release, whoops, okay, and then in this case you can see the biggest release of energy is this, where you actually put the ions together. So this is a sodium plus combining to Cl minus to give you the solid. Okay, and that releases 787 kilojoules per mole. Okay, that's called the lattice energy, or U. Don't ask me why they give it a symbol of U here, but that's usually the most energetically favorable part of forming a salt. Okay, and again, if you just add up everything, so these are all the energies for all those separate steps. If you just add them up, that's where that minus 411 comes from. Okay, so this is just Hess's law over, what is that, 5 different steps. Okay, so pretty complex example. Okay, so the lattice energy, why it releases so much energy, it actually corresponds to the ionic bond strength. Okay, so you need quite a bit of energy to break up these salts. Okay, and so that's why the melting point of ionic compounds is so high. Like it's sometimes 3,000 degrees Celsius or something like that. Okay, so you need quite a bit of energy, and as you'd expect, as you get higher charged ions, then the lattice energy goes up, right? Because these salts are just formed by, opposites attracting, right? So it's just these electrostatic attractions. And so the more this increases and the more that increases, right, in magnitude. So if you have something like I guess it's not on this table, but aluminum nitride is one of the highest melting solids because you've got aluminum 3 plus combined with nitrogen 3 minus. Okay, so they are going to really attract one another. Okay, and so I guess the most they have here is aluminum oxide, where you've got a 3 plus attracted to a 2 minus charge. And look at the lattice energy, right? 16,000 versus sodium chloride is 787. Okay, so if you'd imagine, Hess's law applied to form Al2O3 or aluminum oxide, this step, instead of it being minus 787, it would be minus 16,000. So it would be like way down here, right? So it would be really exothermic. Okay. Okay, so let's talk about the last two types of calculations related to energy here for reactions. And there's the heat of formation. Okay, so the standard heat of formation is how much energy does it take to form 1 mole of a substance from its elements. Okay, and so this is how you would define forming 1 mole of methane. It would require minus like 75 kilojoules. Okay, so it's from its elements. So for you to describe forming water from its elements, so the delta H of formation for water, you'd actually have to write it like this. Whoops, not that. That. Okay, so to form 1 water molecule, you need a half of an oxygen here. Okay, so you wouldn't write it as this, the way we typically do for water, where we balance it. What do we need? 2 of those and 2 of those. Okay, so this is not the expression for delta HF for water, but this one is. Okay, because again, it's just how, describing like forming 1 molecule. Okay. What's important to realize, and these are values that I have to give you. Okay, so you're not going to have to memorize any of these. These are values that you are given, and the delta H of formation for anything in its standard elemental form is 0. Okay, so if you're not given something in a question, then it's not a typo or anything, it's just an element, and so you just assume that it's 0. Okay, and so what we're going to do with these is to get the delta H of a reaction, an overall reaction, you're just going to add up all of the enthalpies of formation for the products and subtract all of the enthalpies for the reactants. Okay, or in other words, final minus initial. Okay, because products are the final state, this is your initial state in a certain reaction. Okay, and so notice here, so this is just some balanced or general balanced equation. You have to multiply the values that you're given by the coefficients here. Okay, so you'll see this in action in the next slide. This looks a lot more complex than it really is. So you're just multiplying these enthalpy values by these coefficients. Okay, So let's see what this looks like. Okay, so this is a balanced reaction, so a very typical question for you. So give you a balanced equation. Always make sure that it's balanced on the exam. So maybe I'll give you one that's not. So then, you first balance it, and then to figure out this value, you need all of these enthalpy values. Okay, so you'll get it from a table. Okay, and the way to set this up, it would be, this is just going to be 0, right? Because oxygen's an element. So you can ixnay that one. So this delta H of reaction is just going to be delta H formation for this C6H12O6 minus all of these reactants. Okay, so the way you do that is it's going to be 6 times the value for CO2. Okay, and then you're going to have 6 times the value for water, and it's liquid water. Okay. Okay, so just plugging in those actual values then. So this is what I just wrote earlier. Okay, so it's just the product. That's 0, so just one product minus all of these ones. Okay, and then you just plug it in. Okay, so it's that minus reactants, and you end up with overall a endothermic reaction, right? So this is saying that it absorbs like 2,800 kilojoules of energy. Okay, notice the units are kilojoules, not kilojoules per mole, because that cancels out, because you're multiplying by these coefficients. The reason why we got rid of oxygen is because it's an element. Okay, so the delta H of any element just by itself is 0. Okay. All right, so any questions about that? So just literally products minus reactants, using values that you're given. Okay. Okay, the last calculation is based on then bond dissociation energies. And so this is something that, again, you'd have to be given, what these different values are. So you'd be given a table, usually an abbreviated table, not this whole thing. And then the way you're going to figure out the enthalpy of the reaction in this case is you're going to look at all of the bonds being broken, which require energy, right? These are endothermic. And then you're going to add up all the bonds that are being formed. And that's going to be negative because these are exothermic. Okay, and then you're just going to add these up. Okay, so you're really just going to set up a little table of all the bonds being broken, all of the bonds being formed, and then just add them up. Okay, so here's an example, a little more complicated one here. Okay, so for this question, these kinds of questions, this is what you're going to have to do. Okay, so you want to first balance, as always. Okay, then you're going to have to, and this is very useful, is draw the Lewis structures of all the reactants and the products. Okay, and that will tell you what types of bonds are being broken and formed. Okay, so for instance, for this one, I would draw it like this. Okay, plus 2 oxygens, so let's put in 2 of them, right? You don't have to put all the dots, but Okay, so you have that. And then CO2, remember, has this Lewis structure. And then water has this. Okay. All right, so that is your overall reaction, okay? Now, you just figure out bonds being broken, bonds being formed. And so you assume in these questions that all of these are being broken apart completely. Okay, in practice, that's really not the way these reactions happen, but for calculation purposes, that's what you assume. So in other words, you assume as far as broken, okay, so bonds broken, is you're going to have 4 CH bonds, okay, and you're going to have 2 O double bonds that are broken. Okay, does everybody see that? Okay. And so then, from a table, you would just look at what those values are. So a CH bond is 410, so that's going to be 4 moles times plus 410 kilojoules per mole. Okay. And then this one is going to be 2 moles. And then an O double bond O is 498 plus 498. Okay, and they're positive values because breaking bonds, you have to absorb energy for that. It takes energy. Okay? So then you can just add these up. Okay, and that'll give you the broken, how much energy does it take to break apart all the reactants? Okay, so that's going to be 4 times 410 is 1640 plus 2 times 498. So that's 996. So that is plus 2636 kilojoules. Okay, so that's how much it takes to break apart. Now, you do the same for these formed. Okay, so bonds formed, and these will all be negative values now. So you are going to form 2 C double bond O's, right? Because then you have 1 molecule, each of those molecules has 2 of those bonds. And so that's going to be 2 moles times a C double bond O is 732. So now it's minus 732 kilojoules per mole because this releases energy, okay? And then you are forming 4 OH bonds, right? So 1, 2, 3, 4. So that's 4 moles. And then an OH bond is, where is it? There, 460 minus 460 kilojoules per mole. Okay, so then we do that. So 2 times 732 is minus 1464 minus 4 times 460, 1840. So that's minus 3304 kilojoules. Okay, so that's how much is released when you break or when you form bonds. This is how much it took to break them apart. So you just add those up. Okay, so therefore overall is equal to 2636 minus 3304. 2636 is minus 668 kilojoules. Okay, overall. So that's your overall reaction. Okay. How come I got a different value? Okay, yeah. Yeah, it's worthwhile noting this value is what we get if we use the bond energies. This is what you get if you do like the previous strategy, right? If you're given these different values from a table, so you're not given any information about what a C double bond O, what that bond strength is, but you're given, what the formation energies are, then you can do, again, products minus reactants, okay? And you end up with minus 890. So, you get different values here. It's quite common because these values are kind of average, and it depends, kind of OH bond in water is different than an OH bond in ethanol, okay? And so these values have a lot more air associated with them. So this value is probably farther from the real one than this one is. Okay, so this is probably a more accurate value because you're actually using these formation enthalpies here. Okay, so those are the two strategies, the two types of calculations then. So if you want to know the enthalpy of a reaction, you can either, if you're given, and it all depends really what you're given. Okay, so if you're given delta HFs, okay, so if you're given that for products and reactants, then you just do delta H of you add up all the enthalpies for the products and subtract, this is just the summation. You add up all the delta H's for all the reactants. Okay, so products minus reactants. Or if you're given individual bond energies or enthalpies, okay, so, and that's easy to spot, right? If you're given like the CH bond is so many kilojoules per mole or something like that, then you do bonds broken and you add up bonds formed. Okay, so I guess the delta H for these, right? Okay, so that'll be positive, that'll be negative. Okay, so those are really the two flavors of questions that you'll see. Okay, and I put some of those on, the Chem 101 as well, so you can give those a shot as well. Okay, so that is it for Chem 131. As I said, I'll be available, shoot me an email anytime, really, between now and the exam if you have questions. But I will have devoted office hours on Friday at 11 o'clock. Okay. All right.